which is one of the key concepts related to dynamics of rigid body or rotational mechanics, as we call it. So let's begin. So what we had discussed on the basis of pure rotation last time, let's quickly recap that. So we had seen that if a rigid body of any shape is rotating about a fixed axis like this, then with respect to some reference axis within the rigid body, like a reference axis like this one, we define angular position, we define angular displacement, we define angular velocity, and we define angular acceleration. Where n cap is the what we call the axial unit vector. And once we had understood the definitions of these terms, next thing which is important is the individual velocity and acceleration of any particle within the rigid body. So once again, within the rigid body, which is rotating about this axis, let's say, okay, if we identify any particle like this particle P over here, then R is the position of that particle with respect to the axis of rotation. So it was important to understand that R is the perpendicular. It is the position of a point or particle.
Sir?
Yes.
Sir, you have taught this in last class.
Yes, I'm taking a recap of this. Yes.
Okay.
With respect to the axis of rotation. So the important thing to understand here is that three-dimensionally, okay, if let's say this is the axis of rotation, this is about which the axis is happening, and the body is some three-dimensional shape like this. So any particle that is located over here, the position vector that we talk about with respect to the axis will be this perpendicular. So basically you can see that mod r is the perpendicular distance of P from the axis. We'll understand this with some examples today. Okay. So having done that, we had seen that if the angular velocity and angular acceleration are known, then the linear velocity of that particle P is given by the cross product relation omega cross r. Say Rp is the position of that particle. Okay. So, and the moment we take mod of this, we get that its linear speed is omega r, circular motion. Okay. You also understand the relationship between the unit vectors. This is the radial unit vector, this is the tangential unit vector, and the axial unit vector n cap is coming out of the plane because it's an anti-clockwise rotation. So we have n cap is equal to r cap cross theta cap, and we have that circular relationship between the three. That therefore r cap will become theta cross n, and theta cap will become n cap cross r cap, like that. Okay. And then we had seen that the acceleration of the particle is the sum of centripetal acceleration plus tangential acceleration. So centripetal acceleration is minus r omega square r cap, which can be written as omega cross v as a cross product, and tangential acceleration is r alpha theta cap, which can be written as alpha cross r. So these cross product relations also become important. So today we'll understand with an example why it's important to understand this cross product kind of relation. Okay. So just go through this section visually once. You have already seen this in the last lecture. If there's any doubt with any of the parts, let me know. Especially the cross products that we're seeing below. Okay, now let's look at, to begin with, a basic level application question. So we have in this next example, we have something rather simple in the form of, like, let's say we have a thin uniform rod, okay, which is lying in the xy plane, rather it's rotating in the xy plane. So let us say this is our z axis and this is the axis of rotation. So it's rotating about the z axis. So rotation is lying in the xy plane. So this is a thin uniform rod, okay, of mass m, length l. So it's rotating in the xy plane with its fixed axis of rotation, which is the z axis in this case, passing through its one end. Okay. So if at some instant angular speed is omega and angular acceleration has a magnitude alpha. Now given that it starts at t equal to 0, okay, with initial angular speed equal to 0, okay, at uniform angular acceleration equal to, let us say, 2 radians per second square, and initially at t equal to 0, the rod was along the x-axis. So it's as in the diagram shown. Here you can understand that the y-axis is coming out of the plane. So it's rotating in the xy plane, but initially it was oriented along the x-axis. Okay. initial angular speed was 0 and angular acceleration is uniform and 2 radians per second square. Also given to us that the length of the rod, let's say this is also given, mass of the rod is 5 kilograms, length of the rod is 2 meters. Now, first of all, what we have to do is we have to find the angular speed and the angular displacement as functions of time. Okay, and also express angular velocity and angular acceleration as vectors in component form, in component notation. And then next what we have to do is we have to find the velocity and acceleration of its center of mass at t equal to 1 second as vectors. That is again in unit vector notation. So this is an application of the concept that we have just seen above, okay, or rather all the physical quantities that we've learned about above. This is a simple example of the application of that. So just try this out, we'll discuss. So people, the first part of the answer, first part of the question, nobody's got. It's pretty simple. See, its angular speed is 0 initially, and its angular acceleration is uniform. So if you just use calculus, you understand that initial angular speed is 0 at t equal to 0, and alpha is 2 radians per second square uniform. Okay. So alpha is this means rate of change of this is uniform. No? So whether you integrate or you just directly understand that uniform rate of change means linear function. Okay, so t equal to 0, initial angular speed is 0, t equal to t, angular speed is omega. So omega becomes equal to 2t radians per second at time t. So this is the angular speed as a function of time. And then the next level of this is that rate of change of angular displacement is 2t. So this time we have to do an integration. 0 to t, 0 to delta theta. So the angular displacement as a function of time has become t square in radians. So actually you can see this is very simple. Like if we had on the one hand 1D motion with uniform acceleration, you have the relation u is equal to, or rather v is equal to u plus at, and s is equal to ut plus half at square. So like that, if we have pure rotation with uniform angular acceleration, then we can similarly write a relation that angular speed at any time is initial angular speed plus alpha t, and angular displacement is omega naught t plus half alpha t square. Like that, like we have the third equation here also. We can also develop a third relation here. Like this. Okay. So you can also think of this as the special case where alpha is 2, omega naught is 0. So omega is equal to omega naught plus alpha t. Okay. Delta theta is like ut plus half at square. So here it's t square. Okay. So here we get this kind of third relation also. So hope this is clear to all of you. Now, once you've got this, we can visualize the motion in the XY plane like this now. That suppose now we take the Z axis coming out. So this was the position of the rod at t equal to 0. Okay. And after some time, the rod would have rotated by some angle. So it would be
Sir,
like
can you
this.
scroll up?
Yeah, I'll scroll up just a moment. So this is the position at some time t. If we take this as a XY plane now, instead of taking it as the, instead of drawing the diagram in the XZ plane, right in the XY plane, you can see that the rotation is happening about the Z axis. So we can see that as angular vectors, alpha will be 2 k cap in radians per second square, because the axis of rotation is k cap, okay, Z axis, and therefore omega will be 2t k cap. Okay. So it started at t equal to 0 with initial angular speed equal to 0, but at some time t the angular speed is 2t. So now we can see that at this instant, the center of mass, which is sitting over here, it will have a velocity vector which is like this.
Sir, that is Z vector, no?
Sorry?
Z axis, no, that is.
Z axis, the axis of rotation is Z axis. So that's why n cap is k cap. The axial unit vector is k cap. Understood?
Yes.
So this will be the angular displacement. Okay, where we understand angular displacement is t square as a function of time. And this will be the velocity of the center of mass. And similarly, the acceleration of the center of mass, when we calculate it, we'll see it will have this kind of a direction, because it will have both tangential component and centripetal component. So acceleration of the center of mass will have a radial component, centripetal component, as well as a tangential component. Okay, so we'll discuss about that. Let's go over this once more. Okay, first part is clear to everyone?
Yes, sir.
Yes, sir, getting it.
Okay, now what we have to do is we have to find the value of velocity of the center of mass and acceleration of the center of mass at the time of 1 second. So let us first of all understand the second part of the question. The angular acceleration and the angular velocities as functions of time expressed as vectors. When you express them as vectors, you have to understand that the axial unit vector is k cap in this case, because the rotation is happening about the z axis. So at any instant t, for example, at t equal to 1 second now, the angular displacement will be 1 radian because it's t square. Okay. The angular velocity will be 2 k cap in radians per second. And the angular acceleration, of course, is constant. It is 2 k cap in radians per second square. Now, at this instant, what is the position of the center of mass? So remember what we had taken the length. We had taken the length as 2 meters. Okay. So the position of the center of mass with respect to the axis of rotation. So RCM is the position of the center of mass with respect to the z axis. Okay. So obviously magnitude of RCM is L by 2. So that is 1 meter. But now at any time theta like this, you can see at any time t, theta is equal to t square. Okay. So the position vector will have a cos delta theta I cap component. Okay, so it will be L by 2 cos theta I cap plus sine theta j cap, where the theta is nothing but the angular displacement, which is t square. So at t equal to 1 second, theta is equal to 1 radian. So the position vector of the center of mass will become 1 meter into cos 1 I cap plus sine 1 j cap. Now 1 radian is equal to 185 pi degrees. It will be close to about 60 degrees. It will be about 57.32 degrees. Okay. So cos 1 radian will be about 0.53 and sine 1 radian will be about 0.83. So this position vector will be approximately cos 1, which is 0.53, and sine 1, which is approximately 0.83 in meters. So now for the third part, why this is important, because we need to calculate acceleration of center of mass and we need to calculate velocity of center of mass. So remember, these are defined in terms of position vector and angular vectors alpha and omega. Okay.
Sir, could you guys scroll up?
For the second part or first part?
For the second part, sir.
Okay, okay.
None, sir.
Okay. So now see, once you got the position vector and angular velocity and angular acceleration, we can see that in general we had the relation that velocity of any point was omega cross r of that point. So now we'll just use that velocity of center of mass is omega cross r of center of mass. So using this, the velocity of center of mass will become that omega, which is 2k cap cross product with this r. So you can see that this velocity vector will be, so k cross I is j, right? And k cross j is minus I. So it will be minus 1.63 I cap, okay, plus 66 j cap in meters per second. Okay. And that you can understand in that diagram, it will look like this. That the angle the rod is making at that moment, t equal to 1 second, is nearly 57 degrees with the x-axis. And the angular speed it is having at that moment is 2 radians per second. Okay. So the center of mass's velocity will be in this sort of direction. You can see it has a negative x component and a positive y component. And you can see that the magnitude, that will just be 2 meters per second. But the direction will be like this according to this vector. Okay, so that is about the velocity of the center of mass. Now, similarly, to find the acceleration of the center of mass, it will be the sum of the centripetal component plus the tangential component. Okay. So the centripetal component is, okay, or what we can also write as omega cross b, and the tangential component is r alpha theta cap, which we can also write as alpha cross r. So we'll express it by this way and use the unit vector notation. So just make a note of this part first, then we'll come to the acceleration part. So basically to
You taken
calculate this
mine.
velocity, yeah.
No, sir, understood.
Sorry, can you speak a little louder, please?
No, sir, nothing, sir.
Yeah.
Sir, you are muted.
So as you can see, people, here we will get the centripetal component of acceleration. So again, k cross I is j and k cross j is minus I. So this time it will be minus 2.12 I cap, and again minus 3.32 j cap. Okay. So this will be the centripetal component of acceleration. And the magnitude of the centripetal component of acceleration will be r omega square or rv, v omega. So this was 2 and omega is 2, so it will become 4 meters per second square. So again, in terms of simple components and geometry, at this time of 1 second, the centripetal component of the acceleration, you can see why it's having a negative x component and a negative y component, has a magnitude of 4 meters per second square. And similarly, now we'll see the tangential component of acceleration. It'll have a magnitude of r alpha. So r was 1 meter and alpha is 1. So tangential acceleration, on the other hand, will have a magnitude of r alpha, which will be 2 meters per second square. But when we calculate it vectorially, tangential acceleration is alpha cross r. So we'll have to take that cross product now. So alpha is also 2 k cap and r is this value 0.53 I cap plus 0.83 j cap. So this will become minus 1.66 I cap plus 1.06 j cap, but this is meters per second square. So it has the same magnitude as speed in terms of the value 2, but this is in meters per second square, whereas the speed was in meters per second. So now the net acceleration, if you want to calculate the vector, the net acceleration of the center of mass is going to become the sum of this centripetal component plus tangential component. So that in the diagram you can see is this vector sum. Okay. So it is for this kind of vector analysis that the cross product method was important, as I was telling you. So just make a note of this, and that completes this question. Now next we will move on from here to another concept related to pure rotation. We'll see how to calculate the kinetic energy of such a rotating body. Then we'll come back to this question, which is why I've given you the mass of the body also. Okay, so this is clear. Now, one more thing we can do here in the calculation is that if you want to find the magnitude of the net acceleration, the acceleration of the center of mass, as we saw, is the vector sum of centripetal plus tangential. But these are mutually perpendicular. So the magnitude of this net acceleration is square root of centripetal square plus tangential square. So that we can calculate without using the entire vector analysis. Second square. So this is a magnitude. But if you want it as a vector, we'll have to add these two component vectors. Okay. Now, next thing we'll understand is how to calculate the kinetic energy of a rigid body in pure rotation. So talking about the general case, if we have an odd shaped rigid body, which is rotating about an axis like this with an instantaneous angular speed omega, then now if we look at any particle at the point P whose position vector is r like this, okay, then we know that its instantaneous velocity so a particle P, it has a speed of r omega, where this r is its perpendicular distance from the axis of rotation. So if this particle has a mass dm, then its kinetic energy now, because it's a particle of differential mass, we'll write the kinetic energy as a differential quantity, will be half dm into Vp square, or half dm into r square omega square. Okay. So now we calculate the total kinetic energy of the rigid body. That will be just the integrated sum of the kinetic energy of all the particles. So it's integration of half dm into r square omega square for the whole body. So now when you want to do this integration, you'll see something interesting, that not only half is a constant, but the term omega square is also a constant. Now, why omega square is a constant is because the angular speed is common. Remember, angular parameters are common for all particles. Okay. So at this given instant, all particles in the rigid body are rotating at common value of omega. Okay. So when we integrate this term next, we can see that we can take that omega square common outside. So the kinetic energy becomes half omega square into integration of r square dm. Now this quantity integration of r square dm is given a special name, and we call it moment of inertia. Just a moment, people. So now you can see that, just wait a second. Yeah, so now what we'll see here is that this quantity r square dm integration, this is a special physical quantity, or you can say physical property of the body, and we call it moment of inertia. Okay. We'll discuss more about moment of inertia. We denote it with the symbol capital I. Okay. So having done that, we see that the kinetic energy of the rigid body is given by the formula half I omega square, where I is this quantity called moment of inertia, which is defined by this. It is integration of r square dm with respect to the axis of rotation. So just make a note of this first. We'll understand more about moment of inertia. As I told you, it's a very important quantity with relation to rigid body dynamics or rotation of a rigid body. And this is the first place where we identify, or where we notice the concept of moment of inertia becomes important. That is when we are writing the expression for kinetic energy of a rigid body in pure rotation. So you'll also see that side by side, if you compare, if we talk about pure translation, then the kinetic energy of the rigid body is defined as half mv square. Similarly, if we talk about now pure rotation, then the kinetic energy is defined as half I omega square. So you can see V is correlated with omega, and similarly mass is correlated with moment of inertia. So this is the inertia property in rotation. Okay, this is the speed property in rotation. In translation, mass is the inertia property, and V or linear speed is the speed related property. So there's a correlation between angular variables and linear variables. Okay, now about moment of inertia. It is defined as the inertia of a rigid body for rotational motion. Okay, about a given axis. So it basically depends on two things. You can see that integration of r squared dm, where r is the perpendicular distance of mass dm from the axis of rotation. So you can see that it depends on the distribution of mass from the axis. So basically what this suggests is that, like, the further away the mass is from the axis of rotation, the heavier it appears to be. Heavier means the more inertia it appears to have. Okay, so that means moment of inertia will be greater for mass distributed such that the distance r is large. Okay, so that is why, for example, if you have something like a rectangular plate like this, and in one case the axis of rotation is here, this is the axis, and let's say this is mass m, length l, and width p. Okay. But in the second case, the same thing is placed like this, and now the axis is this one. So it's the same metallic plate or same rectangular plate having the same dimensions, but in this second case, the moment of inertia will be less than in the first case. Okay. Second case, it will be less than. So moment of inertia in case 1 will be greater than moment of inertia in case 2, because you can see that the distribution of mass is further away from the axis of rotation. Okay, because distribution of mass is more away from the axis. In case 1. Okay, you can see the center of mass is further away with respect to this axis of rotation. So that is like one of the physical attributes of the quantity moment of inertia. Okay. Other than that, of course, it's important to understand that the quantity moment of inertia, it is a scalar quantity. And it has dimensions of ml square, or its unit is kilogram meter square, because it's given by integration of r squared dm. So it's a property of inertia, but that inertia has to do with rotation with respect to an axis. So it doesn't depend only on the mass of the body. It depends on the distribution of the mass with respect to the axis of rotation. So just note down this explanation with this example. And then, of course, we will see how to calculate moment of inertia for different kind of bodies using integration method. So there will be a bit of application of integration in this section of rotation, which is to do with moment of inertia. And we'll see that similar methods of integration we'll be using as we had used in center of mass chapter earlier than this. Okay, so let's understand one very basic example of moment of inertia.
Sir,
Yeah,
could you just show that diagram once again?
yeah.
Done, sir. Got it.
Got it now. Okay. So you understood why moment of inertia is greater in the first case and less in the second case, right?
Yes.
Okay. So now that example we were doing earlier, where the rod was rotating about the z-axis, let's see how we'll calculate moment of inertia in that case. Okay. So next we are going
1
to look
minute,
at,
that last line, can you show please?
sorry.
Sir, can you show that last line please?
Yeah.
Done, sir.
Okay. So next we will look at moment of inertia by integration. So the first example we'll see is moment of inertia for a thin uniform rod. Now suppose, now of course one thing you have to understand, moment of inertia's value depends not only on the rigid body we are talking about, but it also depends on the axis that we have selected. So we will take the axis to be through one end, suppose. So we take the axis of rotation is the perpendicular to the rod at one end. So to calculate moment of inertia, we will of course use this integration formula, that it's integration r squared dm. Now notice that a thin rod, it is a linear mass distribution. Like we had seen in center of mass, there is linear, there is surface and volume. So linear mass distribution means we should take dm as some lambda dl, where lambda is mass per unit length and dl is a length element. So in this case, what we'll do is we will take at some distance, let's say x from the axis, we'll take a thin strip or we'll take a thin section of the rod of thickness dx. So this is a differential section or a differential length dx. So its mass dm will become lambda dx instead of lambda dl. Okay. And mass per unit length is uniform, so it's m by l into dx. Now this can be treated like a particle. So this one is having a distance of how much from the axis of rotation? It's having a distance of x only, because that is the perpendicular distance of that section dm from the axis of rotation. Okay. So now my moment of inertia will become integration of r square dm, will become integration of x square into m by l dx, integrated from the first particle at the axis x equal to 0 to the last particle here at x equal to l. So as you can see, it will become m by l x square dx integration from x equal to 0 to x equal to l. So it will become m by l x cube by 3 from 0 to l. So now completing this integration, the moment of inertia comes out to be ml square by 3. So this is the moment of inertia of a thin rod, but about this type of axis, an axis which is through the end of the rod and perpendicular to its length. Okay. So this is a standard derivation as well as a standard formula. So you should know the derivation steps also for your board level questions, as well as you should know the formula of moment of inertia of the rod by heart. So these examples we are discussing are going to be standard examples. It's important for you to remember the formula as well as the method of calculation. Okay, now if we have the same situation of the rod, but this time the axis of rotation is taken as the center of mass axis, then we'll see we'll get a different value of moment of inertia because the distribution with respect to the axis has changed. The body is the same, the geometry of the body is the same, but because our axis is not through the end anymore, the axis's position has changed. So accordingly, the moment of inertia's value will change. So this is passing through the center.
Sir, this is second case.
Yeah. So this is now moment of inertia for that case where the axis is perpendicular to the rod and through its center instead of through one end. The rod is still the same, mass m and length l. So this time when we take a differential element, so same thing of thickness dx and all that, but for this position we'll take the value of x as minus l by 2, and for this position we'll take the value of x as l by 2. So our limits of integration will change. So when we do this, okay, this will go from x equal to minus l by 2 to x equal to l by 2. So you can